We'll now continue our look at integrating certain types of trigonometric functions, right? So we now have the ability to integrate the 6 basic trig functions. In this video, we're going to turn our attention to powers of sine and cosine, right? So powers of sine and cosine. So essentially, these are the types of integrals that we want to be able to integrate. So something that looks like this. So like the integral of sine to the mth power times cosine to the nth power with respect to x, right? And there are certain key like procedures and identities that are needed depending on whether m and or n are even or odd, right? So before we get into those specifics, I want to remind you of a couple key identities from trig, right? So in fact, again, hopefully these are just reminders, but who knows when was the last time you used these identities. So here are some trigonometric identities that are handy when handling integrals of this form. So we know this basic identity, sine squared plus cosine squared, that's equal to 1. And again, it doesn't have to be just an x, or you might remember it in terms of theta. But basically, I mean, here's the more general representation of this. And again, I'll write it kind of as a placeholder. If you have sine squared of some quantity plus cosine squared of the same quantity, then that has to be equal to 1. Right? So you could have something really complicated in these placeholders, right? But as long as it's the same thing in both of these terms, and your sine is being squared and your cosine is being squared and you're adding it together, then that sum is always going to be 1, right? Again, that's the whole an identity. An identity is a mathematical statement that's true for every variable. So in this case, for every value of x, or for every box, right? This statement is true, right? Now, there are variations on this. Sometimes you might end up in a problem that you have this exact same thing that's on the left-hand side, and it works out nicely when you can just replace it with 1. But sometimes you want to write sine squared in terms of cosine squared, or vice versa, cosine squared in terms of sine squared. So this single identity can be written in several ways. We could say that sine squared is equal to 1 minus cosine squared, or we could say that cosine squared x is 1 minus sine squared x. Some problems, this form is helpful. Some problems, this form is helpful. And we're going to see what those problems look like. I'm basically just reminding you of the identities at the start. That way when we get into a particular problem, I'll say, hey, we're going to use the Pythagorean identity for sine squared plus cosine squared, right? Now you have some other, so these, and I just used the word Pythagorean, right? So Pythagorean identity. You do have some half angle, double angle identities, and these are helpful. The ones I'm about to write down, these are helpful because it allows you to reduce the power on the function, right? And it's these powers that are going to make these problems a little bit trickier, right? Well, in certain instances, using what we call these half angle identities, it's either half or double angle depending on where the form that the equation is in. So here are some half angle identities, one for sine squared and one for cosine squared. It turns out that sine squared can be written as 1/2 of 1 minus cosine of 2x, right? So over here, this power is twice as much as this power, and then over here, this angle, if you will, right, is twice as much as this angle, right? So many times the half angle identity is used if you want to replace sine squared x with something that doesn't have a power of 2, right? And then there's something similar for cosine squared, right? And hopefully these identities are kind of triggering some memories back to trig, right? Triggering the trig. So we have 1 plus cosine of 2x. Right? And now again, these are just the basic forms of these identities. These also can be generalized in a similar manner. So for instance, here is the more general form of this half angle identity for sine squared. Well, if you have the sine squared of something, well, that's the same as 1/2 of 1 minus cosine of 2 times that something, right? So that's where, so whatever expression is here, whenever you utilize this identity, that expression that I'm just symbolizing with a box is doubled on this side, right? So for instance, if you state it just in terms of x, you have an x in parentheses here, and you have to have a 2x in parentheses here. And something similar holds for the other half angle identity. Cosine squared of a box is equal to 1/2 1 plus cosine of 2 times that box, right? Now again, I said it earlier and I'll say it again. I hope that these are things that seem familiar. It shouldn't be the first time you're seeing these, because that doesn't bode well, right? So in other words, you might say, well, yeah, I remember some of these vaguely, and that's fine. A vague recollection, we can work with, but no recollection at all, that's a problem, right? Okay, so let's take a look at the problem at hand now, these powers of sine and cosine. And I'm going to categorize the different processes based on whether or not m and n are even, right? So let's do that first. So if both m and n are even, then we're going to make use of the half angle identities, right? So if m and n are both even, use the half angle identities, right, to reduce the powers on both sine and cosine, right? And they don't have to, both sine and cosine don't have to be in the particular problem, but even if they are, then yes, we have a pair of half angle identities that will allow us to reduce the powers on sine and cosine, right? And part of the reason why we have to do that is you can't treat this like a regular power function. The power rule works for powers of x. It doesn't work for powers of sine of x or cosine of x. Again, it's very, very specific, right? Powers of x, we use our power rule. If we have powers of sine or cosine, that's what this video is explaining, how we handle it, right? So let's do an example, or at least a couple examples of this one, right? So let's see what it looks like. So let's say you have something like sine squared of 3x dx, and you have to find the antiderivative of this. Unfortunately, we can't just add 1 to this power and divide by 3. It doesn't work, right? In fact, if you try it and check your work by differentiation, you will not get back this original thing. You're going to get something a lot more complicated, right? So since this is a power of sine, and since the power is even, then I can utilize my identity, right? So I can express this as another trig function that doesn't have a power of 2. In fact, it will have a power of 1. So let's rewrite this one. So this is the integral. Now sine squared, now it's not just an x that's in parentheses, so that's why we have to apply this more general version of the identity. So my box here in this particular problem represents 3x. So when I rewrite this, I'm going to get 1/2 of the quantity 1 minus cosine of, and now I have to double this, right? So I have to double the expression 3x, and then that gives me 6x. And now here, this is a basic cosine function. Yes, it has a constant in front of the x, but we have a way of dealing with that, right? And now we can proceed with actually doing our integration. So take out the 1/2, and we're left with the integral of 1 minus cosine of 6x dx. And then, so we have a 1/2 there, and the antiderivative of 1 is x. The antiderivative of negative cosine of 6x is negative 1/6. I have to divide by that constant of sine of 6x, and then we have our plus c. Right? So here is our answer for the antiderivative of sine squared. It's 1/2 x minus 1/12 sine of 6x plus c. Right? Now, if this power were a bigger even power, then we would have to apply the identity multiple times. All right. Now, let's do another example of this where it has both sine and cosine. And again, there's several ways that these can work, but I'm going to show you the methods that utilize these half angle identities. So suppose we have sine squared of 4x times cosine squared of 4x dx, right? So now we have both sine and cosine squared, and it's both of 4x in parentheses. Well, we are going to apply the half angle identity for sine squared to this one, and the half angle identity for cosine squared for this one, right? And let's see what happens. So this gets replaced with 1/2 of the quantity 1 minus cosine of, now I have to double this, so that becomes 8x, right? So that's this one. And then let's write down what this becomes. It's 1/2 of the quantity 1 minus cosine, well, I'm sorry, 1 plus cosine, and again we have to double that expression inside the parentheses, so that 4x becomes 8x. All right, and now let's see, we have two factors of 1/2 that we can pull outside the integral. So let's go ahead and do that. So that means we'll have 1/4 outside. And look at what we have left. 1 minus cosine of 8x, and then times the quantity 1 plus cosine of 8x. This is the difference of two squares formula. So what I have here is, if I FOIL this out, right? Because what I have now is a product. So I can't just integrate that factor and multiply them. No, I'm going to have to expand and see what happens. Well, when I expand, I'm going to get 1 minus cosine squared of 8x dx, right? So we're back up to another power of a trig function, but now this only involves cosine. Now we could apply our identity, our half angle identity again, but before I do that, this is where I'm going to utilize the Pythagorean identity and write this as sine squared of 8x, right? So using the Pythagorean identity, 1 minus cosine squared of 8x is the same as sine squared of 8x. And then I'm going to apply my half angle identity for sine squared, because until I get just sine or cosine without an additional power there, I can't write down its antiderivative. So applying it again, what do we have? So we have 1/4. This becomes 1/2, the quantity 1 minus cosine of, now double the 8x, it becomes 16x with respect to x. Factor out another 1/2, so we now have a 1/8 outside, and finally we can write down what this antiderivative is, right? So what we have is the antiderivative of 1 minus cosine of 16x dx, right? So nothing to FOIL out, no more powers of sine or cosine. All we have is cosine to the first power. And then let's write it down. So we end up having 1/8, and then the antiderivative of 1 is x. Antiderivative of minus cosine of 16x is minus 1/16 sine of 16x, and then our plus c. And if we distribute the 1/8, we will have 1/8 x minus 1 over, and what's that? So 16 times 8, so that's 128 sine of 16x plus c, right? So that is the antiderivative of, let's see, where did we start? Sine squared of 4x times cosine squared of 4x. Now every line here, let's count them. 1, 2, 3, 4, 5, and 6 if we include this one. All those 5 or 6 lines, depending if you want to count this last one, this was all trig. There was no calculus until this step right here. So this step is the only step at which we actually applied rules from calculus. Everything else was just trigonometry, right? And that's what you'll find in these particular problems, is that you'll spend 90% of the, or 95% of your work will be based on using identities, different identities, or the same identity multiple times to get it to a form where I now know what basic result from antidifferentiation I am able to use, right? Okay, so that's what it looks like when your powers of sine and cosine are both even. If they're not both even, well, that means at least one of them will be odd, right? And So let's say, so here's our second bullet. Let's say the powers of cosine is odd, right? So let's say, so and remember that was my n. So if n is odd, so if n is odd, then the half angle identities won't work, because those half angle identities only work when you have both powers being even. So we have to come up with a completely different process, right? Right? Let's see. So if n is odd, what we're going to do is this particular process. In fact, let me write it like this. So 1, we're going to split off a factor of the cosine function, and then 2, apply the Pythagorean identities, one of those, right? And it will be clear which one to use based on, the form of the integrand. And then 3, we're going to use the substitution. So use u equals sine of x as a u sub, right? So it turns out in the case where at least one of your powers is odd, the whole idea of this process now is to convert the integral into one to which we can apply a u substitution. All right, so let's see how that works. So let's say we have the integral of sine, let's say, to the 4th power of x, and then we have cosine of, let's say, x to the 3rd power dx, right? So here is that odd power that tells me, oh, I can't use my half angle identity, so I have to do something else. So because the cosine function has the odd power, what we're going to do is this. I'm going to write cosine cubed as cosine squared times cosine. And that's that first step where it says split off a factor of cosine. So write this as cosine squared x times cosine x dx. And it turns out this right here is what we're going to need in order to do a u sub. But in order for the u sub to work, I have to write the remaining factors, or I have to have the remaining factors in terms of sine. So that's why I have to use the Pythagorean identity and write cosine squared as 1 minus sine squared, right? Let's take a look at that. So we have sine of x to the 4th power. Now apply the identity, and cosine squared of x becomes 1 minus sine squared of x. And then I keep my cosine of x dx. Now, since I have these two factors are now in terms of sine, and this differential is in terms of cosine, if I let u be equal to sine x, then my du is cosine of x dx. So what that means is, let's highlight what we can substitute for. So this part here becomes du. The sine to the 4th power, that becomes u to the 4th power. The sine to the 2nd power, that becomes u to the 2nd power. So now I can rewrite the entire integral in terms of u. And this is what it looks like. So we have the integral, so now it's u to the 4th times the quantity 1 minus u squared du. So it's like what we were able to do, right? Because of this odd power and this other procedure now where we were able to factor off a cosine x, use the Pythagorean identity for cosine squared, write it in terms of sine squared. We were able to turn this trig integral into basically a simple power integral. Because all I have to do now is distribute the u to the fourth there, and then I'll be able to use my power rule, right? Because I still have a product, right? I have to distribute that u to the fourth before I use my power rule. So that's what I get when I distribute the u to the fourth. And then let's integrate this. And we're going to end up with 1/5 u to the fifth minus 1/7 u to the seventh plus c. And again, since I don't have any limits of integration, I have to go back and write my final answer in terms of x. So wherever there is a u, we're going to plug in the sine of x. So this is 1/5 sine of x to the fifth power minus 1/7 the sine of x to the seventh power plus c. And then again, I wrote it like this just to kind of emphasize the order of operations, but normally we write, as we've been doing so far, our powers with that notation. Right? And then this is the sine of x to the seventh power, and then our plus c, right? So that's what it looks like if you have an odd power by your as a power of cosine. And it's similar if you have an odd power for sine. In fact, you can have it for both. Let me write down the procedure. If m is odd, so if the power of sine is odd, this is what we're going to do. First thing we're going to do is split off a factor of sine x, right? So split off a factor of sine, right? Whatever it is. And then 2, again, we're going to rewrite the remaining part of it in terms of cosine, right? So use the Pythagorean identity to write the remaining factors in terms of cosine. Why do we do that? So that we can do a u sub, right? And that's the third step, right? Use u equals cosine of x as a substitution, right? And it works even if both powers are odd. Let's wrap this up by doing an example or a final example of where both the powers are odd, and I'll show you what you can do, right? So if both of them are odd, let's say we have something like the sine of 3x to the third power, and then cosine of 3x, let's say, to the fifth power dx. You literally have a choice. Now, how do you choose which one? The algebra tends to be a little bit easier if you choose the function that has the smaller of the two powers, right? Now, if they're both 3, then the amount of algebra is identical, and you have a choice, whichever one you wanted to factor off. So in this case, just to show you what the process looks like by factoring off a factor of sine, I'm going to take the sine cubed and write it as sine squared times sine, right? So let's do that. So this will be sine squared 3x, and then I'm going to write down my cosine to the 5th power 3x, and then put the extra sine factor right beside the dx, right? And then what I have to do now is write this in terms of cosine, right? So that's where I use the Pythagorean identity, and sine squared is 1 minus cosine squared of 3x. But now that's a quantity, so I'm going to put that in parentheses. That's going to multiply cosine of 3x to the 5th power, and then times the sine of 3x, and then times dx. So now what we're going to do is we're going to let u be equal to cosine of 3x. Right? Now, again, this general procedure, it's referring to really whatever your cosine function is. So if there's a cosine of 3x there, that's what I'm going to use as my u sub. Basically, I'm going to replace the entire trig function here that's in terms of cosine. I'm going to make that my u. So let u be equal to the cosine of 3x. So du, don't forget our chain rule, is going to be negative 3 sine of 3x dx. Now in the original problem, or in my integrand, I don't have this negative 3. So we're going to have to divide both sides by negative 3. So it looks like this, negative 1/3 du is equal to the sine of 3x dx. So let's see what gets replaced now. So all of this gets replaced with negative 1/3 du. Cosine to the 5th power, this gets replaced with now u to the 5th power. Cosine squared, that gets replaced with u squared. So again, I'm able to replace all the trigonometric powers with powers of u. So it's like the substitution, it changes it from a trig integral to basically a polynomial type of integral. So this is the integral of 1 minus u squared, that quantity, times u to the 5th, and then times negative 1/3 du. So we can factor out the negative 1/3, we can distribute the u to the 5th, and this is what it looks like. So negative 1/3 times the integral of u to the 5th minus u to the 7th du. So we have our negative 1/3. Now let's write down our integral using, or antiderivatives using our power rule. So this is 1/6 u to the 6th minus 1/8 u to the 8th, and then our plus c, right? If we distribute the negative 1/3, this is what we have, negative 1/18 u to the 6th, and then plus 1 over 24 u to the 8th plus c. And then for our final answer, wherever there's a u, go back and replace it with the cosine of 3x. So our final answer is negative 1/18 cosine of 3x to the 6th power, like that, and then plus 1 over 24 cosine of 3x to the 8th power plus c, right? So there we go. So we now have procedures for integrating different powers of sine or cosine, right? In the next video, we're going to look at what is the process if we have powers of tangent and secant, right? So if you can't wait, hop on over. I'll see you in that video. See you then.